All right, so we're going to cover threads today. We will look back at chess just briefly because I know I threw everybody a little bit of a curveball uh, this morning, but it's not too bad. And the long goal is to make your work on the chess assignment a little less painful. So although I know some of you started, I'll try to talk you through those changes. But then after that, we're going to dive right into threads, which is really all about understanding how to work with a computer that has multiple cores. And all of us these days, except for our phones, are probably working on computers with multiple cores. So these that we have in class have at least 12 cores, which is pretty crazy. And so threads you can roughly think about as being associated with an individual CPU. Now, the operating system, as we'll talk about, will allow us to sort of simulate threads that for which there are no cores. But really, if we have multiple cores, we want to be able to program in interesting ways that take advantage of them because there's a lot of really cool things we can do. So our lab today will be really simple guessing game that's based on the practice problems we're doing. And the idea is we're just going to pick a random number and then we're going to allow our cores or multiple threads to guess as quickly as possible what that number is. And for those of you who follow Bitcoin or digital currency and you know a little bit about Bitcoin mining, that's really kind of what we're doing in a very simplified way here, is just trying to guess a secret number so we can be the winner and then go on and maybe actually do the books for Bitcoin here. But our model is, of course, going to be much, much more simple. So we'll get into that through a number of practice problems, and then you've got your quiz and the big homework 7 due next Tuesday. Okay, so don't forget about those. Those are all good things to get on your grades for Canvas. Now we'll go over Chrono today. Chrono is a huge library that's really powerful and way better than the time library for timing things. And so in particular, when we get into a multi-threaded situation, we'll need a better library for seeing how long things are taking. And really for one thing in particular, for stopping a thread, making it pause and go to sleep for a short period of time. We're going to find that that's a really useful tool for slowing things down so we can figure out what is going on with all of these threads. Now, threads, like so many things we've been talking about this semester, are going to be instances of a class. So we will create an instance of the thread class, and that will represent a computing thread, kind of like its own mini computer, its own sort of almost like its own little world, but all running as part of our main program. So we'll need to create those instances. We'll need to load that library in order to do that, just like we do with vector and with files and things like that. We will also go back to just simple functions. So we are going to need to design some functions that go work on some particular task. And when they're done, they return, and that's the end of their life. And so worker functions are kind of assigned one for one with a thread. So it's sort of think of it like their own private main. So when we write a program with main, but when you work with threads, you need to give them their own individual main that they can go work in. And so they're going to stay in that main for a while, potentially, until they finish whatever that job actually happens to be. So we'll look at some different models for that. And then we'll talk about the really big problem or opportunity with threads is how do you get all these different programs essentially to collaborate without stomping on each other's data? So that requires some special things that allow us to sort of set little signals. You can imagine little lights or flags that say, hey, it's okay to take this, or no, it's not okay to take this. It's kind of like that flag on your mailbox, right? When you want to put something in your mailbox and have the mail person pick it up, you put the flag up, and then they put the flag down, right, after they take the mail. So a mutex and a lock guard is related to that, is all about putting that flag up on the mailbox so that everybody knows that, you know, maybe you shouldn't mess around with what's in there, or maybe it is okay to mess around with what's in there. So that's the main trick to writing good multi-threaded code and really taking advantage of the raw power that you have inside of these computers. Okay. So now, important to just keep in mind that, we don't always have multiple threads. I'm pretty sure our phones don't have multiple threads. A little cheap Arduino computer doesn't have multiple threads. Maybe, the Mars rovers have multiple threads, but I don't know. But certainly our computers do. And if we have a really big problem, usually a math problem or a physics problem or a mechanical engineering problem, and we want to solve it very quickly, we can allocate different pieces of the problem to our cores or threads on our processors and get the job done a lot more quickly. So if we are really competing for time and we're not using multiple threads, then we're probably not using all of the power that's in these modern computers. There's probably some cores sitting there really kind of not fully busy. And if you've ever looked at your performance monitors on your computers, you can actually see how busy the multiple cores might be. It's a pretty fascinating thing to kind of watch. Now, very often the operating system will moderate that. If it sees that one core is not busy, it will try to give it some kind of a task. But that's usually at the high level. Like, hey, you deal with checking the mail. You deal with writing to the file system. You deal with something else. We would like to have finer grain control inside of our programs so that we can be selfish and grab all those cores for ourselves and use them to solve some kind of an interesting problem. So we'll start out with some simpler problems just so we can kind of get our bearings on this. And the scope of our class is such that we can't get really into too much of the math. But what we'll cover in this lecture and the next one will give you a glimpse of all of the really cool things we can do with these really modern multi-core processors that we have lying around. So just a couple quick things and then into a quick review of our chess changes, and then we'll dive into the threading stuff. So remember that the key to getting polymorphism is to collect pointers to anything. But typically we have some collector that is the base class pointer, and then we can collect any derived class pointers in that data structure, whether it's an array or it's a vector. Here we're using a vector because that's, of course, pretty modern and elegant. And we have to have that virtual keyword in front of the method that we want to sort of, automatically or dynamically modulate, right? Do I use the derived one or do I use the base class one? So we've seen that, we talked about that. And it's really very key because we don't want to have to write code that says, if this is an ORC, then do one thing, else do something else. We want to actually call one move method that works the same for all of them, or at least we call it the same, and it just behaves a little differently depending on what derived character we're dealing with in that case. So you'll certainly be doing that with your chess pieces. That's the whole point of that exercise. So your is legal move two in chess is that sort of virtual method. Okay. So we'll want to be working with pointers for that, all of that stuff. Okay. So we kind of saw that we can make our base class abstract, or, by making one of its methods pure virtual. In other languages, there's a keyword abstract, I believe in Java, where you're literally using a keyword that says, hey, this is an abstract class. So C++, we just have a slightly more cryptic way of actually doing that, okay? But very often we make the base class abstract because we don't want it to be kind of showing up in our code, okay? An interface class is even more stripped out. We talked about that last time. No data members and no constructors inside of an interface class. So it's just a tool that software architects use to communicate with everybody what the rules are. And then those other developers can take that and kind of run with that class and add what needs to be added. Okay. Now we looked at the very end last time about the using feature. It just allows us to rewire something that was protected into maybe a more private or public kind of setting in the derived class. Not a big deal. It just sort of changes the registration of a particular method so that the derived class can really change how it's accessed out in the real world. Okay. And so I think some of you saw that in your lab 27 from Tuesday. Okay. So that is the using. Okay. I'll leave you to kind of dig into that. And then the other problem we talked about, and this will lead us to our chess conversation here real quick, because I goofed this up when I put out your original starter code. So we said that when we have a person kind of at the top of this diamond shape here, that creates problems. And we have to incorporate a virtual keyword into the derivation syntax when we do the derivation of the student and the teacher. Okay, not the grad student here, but these just below this one need to have that virtual inheritance or virtual derivation statement in there. Okay, and that solves the problem of having two copies of the person in there. So looking at the code, you can kind of see there, and this would be the equivalent of the rook and the bishop. So if the rook and the bishop are going to participate in a hierarchy where the queen derives from both of them, so the queen would be the equivalent of our grad student here, right? We need to put the public virtual in these two classes that come directly below the base class. And so that was the thing that I left out. Can't believe I left it out, but I think I've got that in there correctly now. And you can see we don't have to have the virtual over here in the grad class, just needs to be in the two classes that are directly below the base class there to avoid that diamond problem or that ambiguous stuff, okay? So let me talk about briefly what I changed. It's not as bad maybe as it sounds. You can start over again from a brand new pro or Replit link if you like, and just copy in your code if you like that. I apologize for making you do that. Or you can individually kind of pull in the code from these changes if you already gotten kind of comfortable with your code. So here's the stuff that's mostly changed. So the .h files have the multi-inheritance code added. So there's a few things that needed to get added to queen, rook, and bishop. Okay, so those can just be copied over. The chessboard has a cosmetic change. I apologize. I had listed the bonuses 10 points each, but it's 5 points each for the bonus stuff there. So I was just cleaning that up in the comments section of the .h and the .cpp. So nothing really changing there otherwise. Piece.extra, I got rid of an extra constructor that didn't need to be there and added some default values. So that's a minor change really. And piece.cpp is probably the most helpful change because it takes care of your end piece logic. So that is going to really simplify your logic for is legal move to. And I'll show you that in just a second on the bishop. Okay. So there's some stuff added there. And there's some what if logic, assuming you're going to pursue the bonus methods. But if you don't, then you don't even really need to worry about that. But if you are thinking about going after the bonus stuff, you're going to very much want to update your piece.cpp. Okay. Chessboard, again, cosmetic changes. And then this one and this one, the last two are critical. You want to update both of those files. Okay. So again, in totality, you could just start over by making a copy of one of these and then copying in your .cpp changes carefully for your is legal move to, because that really should be all you need to be writing in these different derived pieces. Okay. So let me just quickly breeze over the changes. So the things here in background blue is really the only thing that's changed in the bishop.h. We brought in that virtual to the derivation, added it to the destructor and the is legal move to because we are deriving dynamically in the inheritance chain from piece to bishop to queen, right? So we had to add this to that is legal move to so the queen can get the right behavior there, okay? So that's our bishop.h change. So you can kind of either copy it in or just grab the file. Same with a rook, right? Because it's part of that diamond kind of hierarchy. So very similar changes there. Okay. And then that's our, oh, how do I have the rook in there twice? Oh, this is supposed to be the queen. Sorry, this is the queen. Okay. So the queen has a minor change. And this, this is most of the work, right? Public bishop, public rook. We're inheriting from two parents, and that's really all we have to do. We have to incorporate that in there. Okay. So those are all in that updated uh, um, REPL or playground if you're working with Program IZ Pro. Now, let's take a look at the bishop again and see what has gotten easier. So we're still going to want to check if it's a diagonal move, return false. If the area between the row, the from location, and the to location is blocked, return false. Okay. But we don't have to worry about this end piece anymore. This part right here is going to go away, right? So that whole thing in the middle there is no longer necessary because it's really common logic and the base class can deal with this, right? The base class can look and see, oh, you're trying to capture your own piece, right? That's not okay. So you do not have to worry about that anymore. And so that really simplifies some of your piece logic, right? So all we're really doing is determining whether it's clear, right? And whether it's moving at a 45-degree angle. And that is that for the bishop, okay? So hopefully you could carry that logic over to the rook pretty quickly. And then you can combine those two and knock the queen out very quickly. And then slowly work on the knight and the king and the pawn. And should not be a ton of code, but there's lots and lots of ways to actually do that. So don't worry if you find yourself writing a lot of code. Just think through it logically, okay? Questions on that stuff so far? Okay, all right, well, let's dive into our stuff for today. I really like this stuff myself. I try to, think of all sorts of ways to, test my understanding of threading with simple ideas. One of the things that really helps that is being able to measure elapsed time and to put a thread to sleep. So the chrono library is going to help us do that. And it's a pretty comprehensive library. It's a very serious, powerful library. It's got a system clock, something called a steady clock, and something called a high resolution clock. So we're going to be working with the steady clock. It's just a nice way to slow down or stop a thread in mid execution. Kind of like when you do a CN. When you stop and you say, hey, user, give me an integer, we are stopping the thread. That is our main program. Our program runs in its own single thread. And so we're going to be using some stuff from steady clock to help do that and also to measure some elapsed time, okay? And if you're really fascinated about this library, this is a really comprehensive talk. I think that video is still there. It's been out there for a while, but it's really quite impressive. The hardest part about Chrono is just remembering how to call the functions or how to create an instance of a time point for this really long sequence of namespaces. They're kind of hierarchical: STD, Chrono, steady clock, instance of the time point class. So here we're saying T1 is a variable that represents a point in time. So that whole mess is there just so we can get a variable that we can eventually set to a point in time, okay? So STD chrono kind of helps us do that. But if we, of course, have our using namespace STD, we can get away with just chrono, right? So we've taken the STD off of there. Or we can up our namespace if we want to, but that just might be a little too dangerous. So we're going to just kind of stick with using namespace STD for today to kind of get ourselves kind of warmed up, okay? So what do we do with this library? We kind of have this idea of time always flowing forward. Okay, and I've probably talked to you guys before about how time on the internet started at midnight in 1970, and it's always marching forward, and we're counting seconds. And that's a lot of seconds, but it's not more than we can store in an integer variable. We have lots of space for counting more seconds. So that's how a steady clock works. We create a time point and we set it to now. So we're saying T1 equals now, but we have to fully qualify where that now comes from in terms of its namespace. Okay, so that's our T1. And we'll do something that takes time, like calculate square roots or who knows what, and we want to measure elapsed time. We take another time sample, and then we got to create a duration, which is its own thing. So our time span duration of double type is T2 minus T1. Okay, so we can just do that subtraction between two instances. So the minus here is an overloaded operator in the steady clock class. Okay, so or in the time clock, a time point class. So we're not going to dwell on that, but we should all kind of know what that means given the stuff that we've covered so far. And so now we can just say, hey, what is the count? You know, how many doubles are in there? Okay. So it should print out that value so we can see what that is. Okay. So let's just take a look at this, how this thing runs, right? We're just going to run it. There's no programming needed here, but it's a little spelling test, kind of, or a speed typing test. Let me carefully do this so I don't lose my link. Oof, it's bright. Sorry about that. Okay. So the idea with this one, actually, we don't really need to see the code too much. There's nothing for you to really do. We're just sort of taking a sample at now, asking the user to type in a value. Okay. So users are slow. So then we're going to, oh, yeah, we do have to actually create our sample time point here. Okay. So let me give you the code for that so we can kind of keep going at a reasonable pace here. So see if you can create your T2, right? At the bottom, set it to time clock now, right? Steady clock now. Get your duration and do the subtraction on those two things. Okay. And you should be able to print out how long it takes you to type that word. Now you can type anything you want. You don't have to type Mississippi, but it gives you an opportunity to see how long it takes to actually do that. Okay. Let me leave that up there for a moment so you have that code as a reference. I'm going to let you guys tackle that one on your own for this one. And while you're doing this, think about the idea that main is its own thread. And we're putting the thread to sleep right here, okay? So time keeps marching on, but your program is going to pause right here while the human does something, right? So we're moving, 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 and then we pause the thread to wait for a slow human, and then we start again, okay? And that's the time, obviously, that we're measuring between these two sample points, okay? Now, there are other ways to pause a thread, but we're going to stay away from those other ways because Chrono is going to give us, and the thread library is going to give us what we need to do it in a very thread safe way, okay? But that's just a little warm up to kind of get you familiar with that library because we're going to be using that syntax in a few places. Okay. So keep in mind that these are our basically pause points for our main thread, right? And inevitably, in order for our program to finish, it has to get down to here, right? As we well know, okay? So just a couple things. I won't dwell on this too much, but there's just a lot of syntax here. The point is not so much to memorize syntax, just the idea about time flowing on the thread, okay? And that namespaces can be hierarchical, okay? So let's look at another one. This one's actually more useful probably for what we're going to do today. It's called the sleep for function. So as you can imagine, we want to put the current thread that we're in to sleep. So think of this as a delay. Most, like an Arduino or some other libraries, will have something called sleep or delay. So this is called sleep for, okay? And we'll use it in our threads here in a minute, but we need to include the thread library. And all we need to do is sort of express the function call and then put some value in there. So the chrono library gives us some really handy ways of either speaking in milliseconds or seconds or anything. So 6 times 1,000 milliseconds is going to be 6 seconds. But we could also just say chrono double underscore seconds 6. So instead of doing the CN on your last practice problem, you could replace it with the sleep for and just put the thread to sleep that way, right? So really it's kind of a proxy for asking a slow human for some feedback. But we're going to use this in a lot of our practice problems today, okay? And you can choose lots of different, management units if you want, but sometimes seconds is the easiest way to think about things, okay? Or microseconds is pretty standard as well. Okay, so those are our tools, chrono and thread. So let's look at the thread library. So, and let's symbolically talk about what we've kind of just seen. So main kind of processes along a path until it hits the CN, and it has to pause and wait for the slow human to give us feedback. And then the thread continues on again, right? And then there's another pause, right, where we get some feedback, or maybe we call a function, right? And the function maybe computes some things, and it's pretty fast, but it's going to take time, especially if it's, doing a lot of number crunching. And then we continue, maybe we construct something, right? All these things ultimately add up to time. And if our constructor needs to load something from a file, for example, like 1,000 words or 100,000 words, that's going to take slow time as well. So of course our main thread can't finish until the file system gives us what we want from the file, the constructor finishes, and then we can continue and we get to the end of our program, okay? So that, of course, is the flow for every program. We ultimately get to the end, even though there might be some delays on the way, okay? So that's one thread. We've kind of been working in one thread the whole time. We just didn't really realize it, okay? Um, what we want to be able to do is have multiple threads, but we need to have a chief conductor that actually manages all those from inside of one program. We want to be able to have little worker bees that we send off to do things. So our main thread is kind of going to be that conductor, and every other thread we create needs to somehow be attached so we can sort of get the report back or maybe the work back from that particular worker bee. But otherwise we want them to be able to go do their job independently. Go do your thing, come back to me when you're done. Kind of, so we can kind of all relate to that. And we can have as many of these as we want. We can have 4 or 40. Our computers really only have maybe 6, 8, or 12 cores. So really beyond 12, we're not going to see a lot of advantage to having a lot of threads, but it could be a really convenient way to program. Let's say you wanted 100 worker bees, right? Because you just want to simulate what it's like to have 100 worker bees all working independently. Well, you can do that with 100 threads. It just won't go any faster than maybe when you had 12 worker bees. But it's a really cool way to actually think about solving problems, right? So it's like, hey, what is the work that I want to get done? Can I separate it so that it can be done in parallel? So when we talk about parallelism or multi-threaded parallelism, what we're talking about is, hey, we could all divide this problem up and work at the same time, as if each one of us is its own computer. And at the end, our main thread puts all the mathematical pieces together and maybe solves a smaller part of the problem. So real-time physics systems actually work that way. There's a lot of the contact forces that can be evaluated in parallel in large systems, right? So if things are kind of interacting in little islands, those islands can be computed on separate processors. And at the end, all of the forces can be resolved and everything can be moved forward a little in a little smidgen slice of time, right? So there's lots and lots of problems we could work in parallel on to make things go a lot faster, okay? But it does require that we just think differently about the problem. So let's take a look at how we actually get this thing going. So the fundamental worker here is an instance of the thread class, and it's going to have some arguments, okay? So once again, we see we're creating an instance of a thing, right, by sending it constructor arguments, and it's going to be around for a while until it goes out of scope, okay? And the thing that we want to send it is a pointer to a function. So we don't want to call the function, we want to send the name of the function. So if our function is called do work int val, then I'm just going to give it the do work name, comma, whatever the arguments are that I want to pass into the do work function. And the thread will actually launch the do work function from inside of its constructor. Okay. So we don't launch the do work. The my thread one will actually do that for us, and it will feed it that argument, right? As if it was going right into there. So we're really just handing it over and saying, hey, you do it, right? When you're ready. Okay. So we can send that same worker function to as many threads as we want, because functions we kind of know execute on a stack. So this do worker function in this case is going to work in a completely different space than this one does over here. They have the same logic, but they're going to be like their own separate main programs. Well, how do they behave differently? It all depends on what we feed into their arguments, right? So here we're giving a value of 20 versus a value of 10. And those things are going to do whatever they're going to do inside of those individual threads, okay? And so sometimes it's really good to have that be the same function because you know you're doing some kind of symmetric processing. Maybe you're determining whether two objects are touching or have interpenetrated each other, like two spheres or something, right? If it was a physics-based system. So, but that's, sometimes a very good thing. But we don't have to use the same worker functions all the time. It really depends on the problem that we're trying to solve. So here's kind of how I think of this. At some point, we launch a thread. We say, hey, here's your do worker function, you go, right? And main does not stop to wait for that thing to finish. It marches on immediately, okay? And so main says, okay, I'm going to launch another thread. Okay, now that one's off and running, okay? And then maybe main stops to get some feedback from the user for some reason. But at some point, we have to put up a little sign for our threads to come back home again. So that's what we call joining or rejoining. So we want those threads to sort of rejoin at some point in our main thread. And if they're not done, we will wait right there, exactly right there like a CN. We will not pass that line of code where we say join. So we would say blocked or locked, waiting for thread 2 to come back. As soon as thread 2 comes back from its job, we then can wait on the next thread, okay? And once those two threads have rejoined, then we actually get to finish our program, okay? So we don't know what's going to happen in here necessarily or how long it's going to take. We're just going to sit here and wait and then wait, okay? And if this one never comes back, then we never finish our program. And if this one never comes back, we never finish our program. That's what we call thread lock. So there are strategies we will learn to follow to make sure that those things do come back and rejoin us, okay? So one thread, one worker function. That's kind of the nice way to start thinking about it. So let's look at a really, really simple worker function. Do work, and I'll say for I equals 0 to less than max, print a little message, and then go to sleep for 1 second. So it's kind of like we're doing actual work there, and it takes 1 second to do 1 unit of work. So that's going to be our super simple worker function. So once that thing has kind of cranked through however many seconds of work we've given it, then it will finish and it will rejoin our main thread. Okay. So that's about as simple as we can get it. And we could set that sleep to anything, but if we set it to 0, it's a little harder to debug our code, right? Sometimes we want to set it to 0 and have no sleep, but we'll put a sleep of 1 in there for now, okay? And remember that our thread is an instance of the class. So it's got methods, it's got a constructor, right? Our instance is the variable essentially that we're creating. And our constructor needs these arguments, right? And no parentheses there. We're just passing in the name of the function, which is essentially a pointer in C++. Okay. So no parentheses, because we don't want to call the function. We want the constructor for the thread class to call the function. And these are our primary methods, right? We can do some Boolean test, or we can rejoin or detach or swap. And then we can check and see whether certain things are, or we can assign rather. That's not an equivalence. It's an assignment operator. Okay, so that's our assignment overload. Okay, so let's do that, right? Let's set up a do work thread, right? We'll pass the do work function in, we'll print a message, and then we'll rejoin that thread back at main. And we'll just sort of start with one thread and see how that goes. And if you get that working, you can expand to multiple threads. Okay, so let's see if we can do this one together. Okay, so here's our worker function. It's going to sleep for a little bit, and it's going to print out what thing it's working on. So let's create a thread. Thread is the class name. I'm just going to call it T1. I'm going to give it do work. And what am I supposed to do? I guess I can give it any number I want. Let's just give it a 5. Okay. So I think that's what we're doing here, right? We're going to give it a 5. So that's how much work we want it to do. Okay. And we're going to print a message here just to help us debug, right? See out. Waiting for the thread to finish. Okay. So that's where it's doing its work. And then we'll say t1.join. Okay. That's bringing it back. And then we can say cout. All done. Okay. Okay. So let's see if I got that part right. It's not too many steps to that. Okay. Up. I missed something do work. I can't even the little things. Okay. Okay, so there we are, right? So we're sleeping 1 each time, and you can futz around with that number and see that it goes faster or slower, of course. But if you set it to 0, right, in here, it's going to go by pretty darn fast, and it's kind of hard to really realize the mechanics of what's going on here, right? So that's kind of a little bit, it's like, so what, right? But when we kind of slow it down, things become a little bit easier to visualize, okay? But that's just one thread. Okay, so let's see if we can do another thread. Okay, just while we're at it. Right? So go to main. It's just that easy. So we'll do another thread, and we'll give this one kind of a different amount of work to do. So we'll give this one 10 things. Okay, same function, different amount of work. Okay, and now we'll say waiting for the thread. We'll say waiting for thread 1 to finish. Okay. And I will just steal that and copy paste. Okay. And I will say waiting for thread 2 to finish. Okay. Thread 2. Like that. Oh, I got to change this to a 2. Okay. 2 and a 2. Okay. So this is our rejoining of thread 1. This is our rejoining of thread 2. And we're all done. Okay. So let's see what actually happens. Now, one thing you notice right away, it's kind of hard to tell which one is which, right? So doing work 0 is coming from one thread, doing work 0 is from the other thread. And here we see waiting for thread 2 to finish. That means thread 1 finished, right? So that's pretty good. But now here comes the rest of the work for thread 2, okay? And we're all done. So you can see pretty quickly it gets tempting to be like, maybe I'm going to add a little message, right? String, you don't have to do this, but string name, right? And so I'll say, name is doing work, right? And I'll put in a little connector. Okay, and now when I send in my do work, I'll just say A and B, okay? These are my threads A and B. Okay. Now it's a little bit easier to kind of differentiate. A is doing work. You can kind of see they're just spitting stuff out, racing right along here in separate threads, doing their own thing. And then B, of course, has a little more work to do, so it's going to last a little longer. Okay. So pretty cool that we can do that. And your imagination starts to run wild pretty quickly. It's like, huh, what in the real world works like this that I could sort of simulate, you know? And I don't really have to worry about syncing them up in the normal way. Like I don't have to return from a function and then go do some other thing. It's all happening kind of in parallel, which is pretty cool. The key thing is we've got to rejoin for every thread. If we forget to do that, of course, we have some problems, right? We're going to crash essentially, right? If we don't rejoin. Just so you're familiar what that crash looks like, I'll just leave one of them out here. Okay. So we looks like we didn't even get to the running of it actually. Is it really that sensitive? Huh. Oh, something's not right here. Mhm. Well, I've probably gone one step too far here, or probably confused program IZ. But any case, you want to make sure you rejoin those so that we actually don't get that crash. Okay. Okay. So that's our just, walk, crawl, walk, run start of all of that. Okay. And sometimes you may notice that your printout gets garbled. So two threads can write to the console at the same time and stomp all over each other. So you might get garbage printout because the two different couts kind of get mixed together at the same time. There's nothing in the output window at the moment that's preventing them from shoving data out at the exact right time. So you can get some hard to read output there. Okay, so let's take it up a notch. Kind of pretty similar to what we just talked about. Let's create a worker function called cast spell. We'll say the name of the spell and how long we think it should take. So we've probably all played some kind of game where there's some crafting going on here, right? So our thread one is going to cast an abracadabra spell that should take 5 minutes, right? And we want to make sure we rejoin those threads, okay? And then we'll see, which one is going to finish. And you can play around with different simulations on this, but let's just take a look at this one here. Okay. Okay, so here's our, let's just skip to the fun stuff here. Here's our worker function, right? So we're going to bring in a sleep for, and we're going to use a variable number of seconds here. Okay. Okay. And we can add our message here just so we know what's going on. See out, working on spell name. Okay. Yeah. Okay. Or we can say done with spell name. That's an important insight, right? By the time we get to that point, the spell is done. Okay. So we could add two of those if you want. Oh, we are doing that. We've got that here already, right? Okay. So here's our two spells. Add whatever you want there. So here's our first one. Cast spell, spell one name for 5 seconds. Right. We'll add a second spell. Okay. Okay. T2. Okay. And we'll do spell 2 on this one. And we'll make this one for a shorter amount of time. Whoops. All right. So maybe, wait, give that 2 seconds. Okay. And then we got to rejoin. So T1.join, T2.join. Okay. All right. And see out all done. So just as a reminder, this spot in here, we're still waiting for spell number 2 to finish. So let's just write a message there. Still waiting. Well, we don't know which one we're waiting for. Well, actually, we do know which one we're waiting for. We're still waiting for spell 2 to finish. Okay. Yeah. Okay. And then here, let's say, still waiting for spell 1. Okay. So let's just see how that shakes out. If I get that right. Ah, doggone. Okay. What did I goof up here? Did it say? Um, So thinks that's not a comment. What line was that on? Line 33. Huh. Oh, sorry. Yeah, no, that should work. What am I? All right. I'm not seeing it. A matching function called sleep for int ampersand. Seconds. 8 seconds. I just called it wrong. Sorry? Oh, thank you. Right. Oh yeah, I put in an extra argument there. Thank you. Right. Cast spell. Oh no. The the second argument is time, isn't it? Sorry. Let's see. Well, our first argument should be our worker function, right? So there's our worker function. Spell 1, spell 2 is the argument for that. All right. I guess I'm a little short on sleep. Cast spell 1, spell 2, 5.
You just forgot to put chrono seconds and then seconds in the parentheses.
Oh, thank you. Right. Okay. Right. Oh, sleep 4. Right. There it is. Thank you. Okay. I think, yeah, you guys were helping me out and I just wasn't hearing it. Okay. I think I did this earlier today too. And I was just, thank you. Uh, oh, oh gosh. All right. Thank you. Thank you. Please. Okay. There we go. Okay. Yeah, that was really painful. All right. There we go. So we're going to wait on each of these in the order we rejoin, right? Even though one of them might be finishing before that. That was kind of the whole thing I was trying to get to there. So pretty similar to the last one we looked at, but using the same worker function for both of those things. Okay. And we want to make sure we join so we don't do the crash. Now, we can have lots and lots of these things, and they don't always have to be the same worker function. So here's another way of thinking about things. Let's say we have a lot of different jobs to do, and they have some sort of dependency to them, right? We want to build the tires, we want to build the engine, we want to build the chassis, and once those things are all done, we want to rejoin and then maybe pull together some of that data and do one more process. So let's just take a quick look at this one. All we're really going to do here for this, I'll show you the code for the solution here and let you guys dig into it while I recover. So basically, we're going to build the tires, build the engine, build the chassis, and just let those processes go do whatever they got to do, however long it takes. Okay. Rejoin, and then after the rejoin point, we'll call one more assemble thread there on the back end. Okay. So we should be able to rejoin these things in any particular order. Okay, so let's take a look at this here. Okay, so here's us building the tires, the engine, the chassis, 3 different worker functions for different spans of time, and then sort of rejoining these things. Okay. And then assembling the parts, launching another thread, maybe because there's some data that we need to rely on that didn't get finished until that point. And then we can call that final worker function to finish and then rejoin. Okay. And done. So let me give you guys a minute to give that a try. And for those of you who took algorithms and you remember dependency graphs, right? Or a topological graph of or traversal of a graph, right? You can imagine that we could model some pretty complex processes and then simulate those things, you know? Okay. So just keep in mind that we're waiting at each of those join points, right? Before we can continue, okay? That's the key bit there, okay? So if we're out of order, actually, I think there are some situations in which we could have some thread lock. We'll probably talk about that on Tuesday if we rejoin in a strange order versus how we actually launch those threads. We'll talk about that when we come back to round 2 on this next week, okay? But you might start to see some of this output sort of stomping on itself and getting a little confusing, okay? So for example, if you see building, engine 0, done, tire, pound 5, that's 2 completely different output or couts coming from 2 threads that are running in parallel. And that's just because our output console isn't really thread safe, right? We need to come up with a different way of actually printing that information out. That's a little more clever. Okay. Now, the big thing that's interesting is figuring out how to deal with data. So let's talk about this idea of managing inventory. So if our threads needed to cooperate and just maybe sell some inventory, right? There's some integer value that each of the threads wants to steal 1 unit from each time, right? So let's say we're selling grommets and we would like to sell 10 of those grommets, right? So a worker function, let's say a salesperson, right, wants to check the inventory and try to fulfill an order for 10 grommets. So of course they want to check if there's enough of them, more than 10, and then go ahead and subtract the appropriate amount. In this case, we're going to just subtract 1 unit at a time rather than a whole bunch, right? But we could have a situation where lots of threads are competing for the same piece of memory, and we cannot really rely on the fact that those threads are not going to try to grab the same unit of grommets and sell it at the same time. And we'll kind of look at that here in a second. But let's model our worker function. So we're going to say in a naive way, right? So this isn't the final solution, but we'll have the name of a salesperson, a pointer to our inventory, right? So we're going to pass in now an address rather than using a global variable. We'll pass in the address of some shared inventory and how long it should take that particular salesperson to close that particular sale, let's say, okay? So our first approach might be while the integer at that address is greater than 0, declare that we sold that particular unit. So in this case, every number is kind of what unit of inventory we sold, okay? And then we'll decrement that inventory, okay? So now we've reduced that and we sleep for our delay because that's us recovering from that sale. And then we wrap around again and try to sell some more, okay? Not a bad first start to modeling a sales process, okay? And so the inventory number should represent what's left, and the ID is kind of like the one that we sold so far, okay? So just to kind of keep things in mind. So here's our thread for a salesperson. We pass in the address of our grommets, right, to all of our salespeople, and we give them 0 seconds delay. So nobody needs to recover at all when they first start this process, okay? So what we're going to see is that these salespeople are going to kind of cheat, right? So what's going to happen is there's a key moment here. So when we find out that there's inventory in our logic check, there's a brief moment in time where another thread reaches in there in an out of sync or asynchronous way and takes that inventory from us. So we don't know that because we had just checked that thing a moment ago. And so we will also decrement the inventory and print a message about it, okay? But what happens now is we have negative inventory, okay? So this little tiny gap, this window of time here between when I check the inventory and when I actually decrement the inventory, the other thread is stealing the inventory, okay? So this is the problem with working with shared data between these threads. They really don't cooperate as if they're part of the same program because we have multiple threads, multiple execution lines of logic. Okay. So we need a way to solve that problem. So let's just take a look at what it looks like. There's no coding required in this, but let's see what actually happens, right? And we should be seeing some negative totals, and we should be seeing multiple salespeople selling the same thing, okay? So we got 100 things here, and we see, oh, this is interesting. So A sold things for a while, and then D sold something for a while, and C got in there, but then D got back in, right? So some of these threads are kind of succeeding to sell kind of randomly before other ones can, right? But if we get to the bottom, we see we have an inventory of -4. So somebody sold something twice, right? Several times, okay? So that's kind of how that problem manifests itself. If you look at the code, you'd think, well, what did I do wrong, right? But the problem is this little gap between when we check it and when we decrement it, okay? And even that part right there. So we want to be able to fix that, okay? So and again, here's that problem of our output kind of all being jammed out there at the same time. You can kind of see that the output from the different threads gets split together. Okay. So let's see if we could fix this. Okay. So one idea would be to kind of come up with a flag that we could set to say, hey, I've got the flag, right? Don't anybody else like touch this. I've got this. Okay. So we could say, oh, I'll create a variable called is locked, or a pointer to a variable, it's a Boolean variable says is locked. And I could say, well, if it's not locked, then I'll go ahead and I'll lock it, and that should keep me safe, right? And then anybody else who checks that variable will find that it's locked and they won't do anything, right? That's the hope anyway. But the problem is that we still have this little gap of time on our Boolean check. So somebody else could check it and see that it's not locked, and they could lock it thinking they have permission for it. So there's really no, simple way around this particular problem. So that's why we have the mutex. So mutex is a very special class that is able to secure a lock on a particular instance of this mutex class. Okay. So it's a bit of a strange animal. So let me kind of introduce the players here. So the mutex is like a flag that everybody can see, right? Think of it as a global variable. And everybody agrees, all the worker functions agree that they will always check the mutex before they try to change any memory. Okay, so it's really just like a flag. It's not associated directly with any of our memory. It's a thing that we look at like a flag. So it's either going to be unlocked or locked, and I'll represent it kind of that way in my graphics. So any thread that tries to kind of capture the flag is either going to succeed and be able to continue with its work, or it's going to be frozen dead in its tracks. So whenever you try to get a mutex, the rules of the game are, well, you might be lucky and you might not be lucky. If you're lucky, you get the mutex and you just keep marching forward. If you're unlucky, you freeze until the mutex is freed up again. So essentially, every thread that tries to get the mutex and fails will freeze and stop until the mutex becomes available. And then the minute it becomes available, it's a mad dash to see who can get the mutex the next time around, okay? So there's really no official connection between the mutex and your data. It's just an agreed strategy that we're going to use. And we do need to create one of these things so we can check it in our code, okay? So it's a little bit like capture the flag, okay? So our inventory is up here, and we have our mutex, and those two things together can now give us a solution to the problem, right? So if I acquire the mutex, then I know it's safe to go change the inventory because everybody else has agreed to the same rules. All of our worker functions would agree to check that mutex, okay? So here's our mutex. It's as simple as that. It's like a flag, and we'll use it as a global variable for now, just to simplify things. So I will say our inventory is 100 units. I have salesperson A, salesperson B, and I have failed to rejoin my threads here. So that's a little bit sloppy on my part. I'll come back and fix that later on. Okay. So, but we have the one worker function that ensures that we will actually kind of follow the same set of rules. Okay. So we're going to both be checking that same global mutex. Okay. So we do that and then we're off to the races. Okay. So let's take a look at what our function can look like. So the first thing we do, and we're going to do it inside of a while loop because we might fail, right? And have to go around again, or there might be additional inventory. So we'll say, first thing, try to capture the flag, okay? And if I am not lucky, then I will freeze until the flag is available again. So I might be the unlucky thread that can't go forward. But if I do get to go forward, then I can check the inventory and say, hey, I am selling this particular item. I'm decrementing the inventory. I'm going to sleep for a second, which is going to kind of cause everybody else to keep sleeping as well. And then I'm going to unlock the mutex, okay? So now I am available to wrap around and try to grab the mutex again. So it's a free-for-all, and I'm part of the race, right? I took a little nap here. I got rested. I freed up the lock, and then I'm going to loop around and try to get it again. And I'm going to compete with everybody else who's been waiting while I've been using the lock, okay? So I do have a chance in the scenario that I could actually get the lock 2 times in a row. Now, if there's no inventory at all, right? If the inventory that's there is 0, then I just want to unlock and return because I've done my job, okay? So for those of you who decide to do homework 8, we're going to simulate a restaurant with a maitre d' and a cook and a waiter. And each of those individuals would have a worker function, right? And so some of them get to go home earlier than the other ones, right? So maybe the cooks finish cooking everything and the front door is closed and the cooks can go home, right? So we need to be able to know when it's safe to return from our function, right? For our particular worker function, okay? But that's kind of a reasonable working model. And you might think, should this sleep be before or after that inventory lock? What would be the effect of taking your rest after you unlock the mutex for everybody else, right? Versus hanging on to it, okay, while you're napping, okay? So here's a different view of how that's going to go, right? So we have our mutex, right, on thread 1, and we lock it, right? And we get to go do some work. Meanwhile, this thread over here has to sit around and wait. Okay, so it is gone to sleep because it checked the mutex. I finish my work, I unlock, and let's say the inventory is gone, right? I try it again, and at some point, there's no more inventory, so I go back and I rejoin main. And finally, thread 2 wakes up and goes, it's finally my turn, but there's no inventory. Okay, I will go back to main as well, okay? And we really can't control who's going to join when, right? So it really depends. So main will just end up waiting here for whichever one we said we're going to wait for, right? 2 or 1, okay? So that is actually going to work for us, right? So here's our inventory class that's sort of rezzed up a little bit. We're going to create something called inventory, and we're going to keep track of which salesperson sold how many things. So we're going to have a map here, okay? So just a little fancy, who sold what, basically, okay? And then we will have our constructor of how many things are available for sale. So that's going to be our inventory tracker and our sales tracker as well. And then we'll create a mutex, okay? So the mutex is just that little magical flag we all agreed to work with. So let's go put this one together, okay? So let's just jump in and look at the code here. So I think we're doing okay on time, but I'm gonna push the pace just a little bit. Okay, so here is our inventory. We just kind of went through that. So it's a map, right? So key value pair, string, integer, okay? There's our locking mechanism. Okay, so we want to lock the inventory before we check it. So we're going to say, what do we call it again? Inventory mutex.lock. Inventory mutex.lock. Okay, so we're going to lock it, which means we either get it or we freeze right there. Okay, so as soon as we unfreeze, okay, oh, I think these are just global instructions. So I'm going to move them down to here, right? So I'm going to say, I'm going to try to lock the inventory right there. Okay. Then I can check it. I can say, okay, if the inventory quantity available is greater than 0, then let's kind of take one, right? Sell it, take some, right? And then we'll record, right? If the inventory sales of the salesperson does not have a key in the map yet, let's add them and give them 1 unit of sales. If they're already there, just increment their current value that goes with their key name, okay? So this is just a little map exercise for us, okay? And now this person is going to sleep, okay? And at some point, we got to unlock this thing. So where should we unlock it? Okay, because if we don't unlock it, then we're going to have deadlock in our code. So let's say that we're going to unlock it down here. Okay, so after we subtract something, we'll unlock it so everybody else can try, and then we will take a little nap. Okay. But there's this else down here where we have to unlock it as well. If you forget that one, you will be in deadlock because you will return from the function without releasing the lock. Okay. Oh, this is an unlock. Sorry. Unlock. Right. And unlock. Like so. Okay. So let's see what that does. And there's very subtle differences in behavior we might get here by just changing that. So we have salesperson A. Now, I think I need to add some more salespeople. So let's go to main. Yes. So there's just one salesperson. Okay, let's add another one. And we'll have this salesperson B. And notice that nobody is delaying. They're going pretty fast. So let's just give them each a 1 second delay. Okay. And let's see what happens. Okay, whoops. Same one. I gotta make this 2. Okay. 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 So A and B, right? Let's see if we get to the end and we have negative values or not. It doesn't look like we have any duplicates. They're both sort of taking turns nicely, right? Final inventory is 0. A sold 1 more than B did. So this is what people mean when they say thread balancing, right? You want both threads working equally hard, and you don't want one of them necessarily blocking the other and hoarding all of the work, because that means you have some other thread that actually isn't really doing any useful work. So in a multi-processing situation where you have multi-cores, you kind of don't want to go to sleep on the lock, right? So if we move this after that, just kind of interesting to see what happens, right? So we'll move the lock after, so we go to sleep, right? And then we ourselves will compete equally for that other, or for the lock when we loop around, okay? So you can see A is kind of dominating things now, right? Just that little change in the behavior where A kind of holds or sleeps on the lock, right? Ends up giving A some kind of an advantage where B never really gets a hold of the lock, right? So little tiny changes in where you lock and unlock can completely change the behavior there, okay? So we still sold all the inventory, but person B never really got a chance. And we actually took longer to sell all the inventory, right? Because it was just one person doing it instead of having two. Okay. So you can rev up and have as many of these threads as you want and, grind through a lot of inventory. And that's very synonymous or similar to using these multi-cores to solve larger math problems or processing problems that can be divided and conquered that way. Okay. So there's our kind of doing it with three of these. And you can dial these down to zero. Once you get the behavior balanced, you can take the times down to zero and it should hold up, right? It should hold up. You should get a reasonably good result. Okay. But you can kind of play around with that a little bit and see different kind of behaviors. This is a really good one to get comfortable with what's going on in these threading situations. Okay. A lot of behavior changes from just shifting things around a little bit. Okay. And if you forget, let's actually do that. Let's go back and forget to unlock, because this is a really classic error, and I do it too. We're looking at our code and we just don't see it. It's like, oh yeah, I think I got everything handled, but I forgot to unlock if there was no more inventory. So if I do this, see if I even get anything. Actually, it looks like I went into an infinite loop, and so it's not even going to run for me here, or I'm not going to be able to see the output. So we're probably in a thread lock situation there. Okay. So, well, I can guarantee you we are, right? So hard to debug. If you don't know what to look for, you have no idea. You might think, okay, my program somehow is never calling the function, or I don't know what's going on, right? So having print statements in here is probably really, really helpful, like, out of inventory, of inventory. I don't even know if this is going to do it for me, but let's see. Yeah. Okay. So let's see if that even gets executed. Oh, yeah. So this is a little bit hard to debug, but all the more reason to be really careful about that stuff. Okay. Maybe I'm a little bit new with running this stuff in Program IZ, so I don't know if once you crash, you're kind of hosed here and you've got to restart it or not. But heads up on that key point there in any case. Okay. So here's that code kind of laid out. Let's see if there's any highlights. Yeah, I think we kind of touched on all of these things, right? Good. Okay. Okay, so sometimes we can get stuck waiting on the lock. So this we talked about, right? So this is when we forget to unlock, right? So that's just what's happening here, right? We're stuck at this point waiting for number two and it never comes back. Okay, so we never even get to the rejoin point for one. Okay, so that's just a bit of a graphical visualization of that for you. Okay, and we would call that deadlock. And it happens a lot. So if you don't have a goodbye message at the end of your program and you don't see the goodbye, you should be very suspicious, especially when you're working with threads, because you're probably still running. Your program probably didn't stop in a deadlock situation. Okay. Okay, let's see if I can sneak this one in. This is not a really huge point, but it is another important example of how this idea of scope-bound resource management works. So forgetting to unlock the mutex is a pretty common thing. And so folks invented this scope-bound idea, kind of like shared pointers. So notice we're taking our inventory mutex here and we're saying, I'm going to wrap it in a safety bubble, like bubble wrap, and I'm going to call it something. Call it anything you want, right? You could call it bananas if you like, but we're going to call it scope lock, and it is a lock guard of type mutex. So that thing is an instance of a class with a destructor that will unlock that when it goes out of scope. So what we've done here is create an automatic safety mechanism that can be useful for reducing bugs where we have to unlock something when we return from a function. So there's the name of our class, the type that we're locking. We're going to lock a mutex. There are more than one kind of mutex out there. the name of our variable, and then the constructor arguments. And that's the thing we're wrapping in bubble wrap, right? So here's kind of how that looks. Imagine we did that inside of some kind of curly braces here, right? So we just got to do it once. And when we leave that scope, right? So that will acquire the lock or freeze at that point. Okay, either one. It depends on the situation. Okay, because it's our scoped lock guard. And then we can do some work if we do acquire the lock, right? And then at the end of that scope, maybe the end of the function, it's just going to disappear. And its destructor is going to forcibly unlock that thing, okay? So this is our RAII, or scope bound resource management. Same strategy or pattern, or sometimes it's called an idiom, that we use for our shared pointers. When they go out of scope, they clean up the mess. So LockGuard is doing that for us here with the inventory mutex. Okay, so just another way to deal with unlocking a mutex. Okay, so here's a visual implementation of that. Kind of overkill here, but there's our mutex acquired, right? Everybody else has to wait. We do our work. And as soon as we return from the function after eating all the inventory, our lock card goes out of scope. And then the other ones can try to acquire the mutex and sell inventory if there's any left to sell. Okay. So it might not always work for your situation, but it's another tool in our toolbox for us. Okay. So the risk here in this model is the first salesperson to get the lock is probably going to sell all the inventory until they leave the function. So it might not be the best use of our, our current model, right? So here we're acquiring, this is a bit of a problem, right? We don't want to acquire the lock guard over and over and over again because we're getting a lock of a lock of a lock of a lock, and we'll never be able to unwind that. So we want to get the lock guard outside of our while loop. Okay, so we only ever get one, and then we leave the function and it goes away. Okay, so let's see if we can knock this one out real quick, and then we'll get you guys set up on the lab so you can kind of get going with your next thing. Okay, so try doing it outside of the while loop, or create some special scope. Remember that you can just add two curly braces anywhere you want in your code, and that creates scope, right? So you can create that around some critical region. We'll call that the critical section of your code because it's where we acquire the lock. You can get your lock guard here and then do all your work down here. And as soon as your execution leaves those curly braces, it'll go poof, right? So you don't necessarily have to leave the function to trigger that, okay? You just don't want to do this more than once inside of that function, okay? So let's see if we can actually do this, okay? And I really want to get you guys out of here on time. So let's see if we can do this without too many problems, okay? So there's our regular mutex. It's still there, okay? And then we're going to use a lock guard in here. So let's see if we can put our lock guard right here at the top of our function and see what happens, okay? So give you a little help with the code there. Oh, I know it's really small. So std lock guard, std mutex. So let me put it on screen here for you. std lock guard, right? And that's going to be of type std mutex, right? And we can call it anything we want. I will call it my lock, okay? And we are locking the inventory mutex, okay? I think that's what we called it up top, inventory mutex. Okay, and that's it. But that's going to be a really interesting behavior for us. So let's see what happens when we do that. Okay, I think that's really all we have to do. So when we do this, we see that A completely dominates because they acquire the lock and keep going until they completely eat up all the inventory. So maybe not a very balanced compute situation, okay? So what we could do, I don't know exactly what this will do, but we could kind of create a scope inside of the while loop here. So there's the end of my while. This will be end of lock scope, okay? And we'll move our mutex into that, okay? So let's just take that, okay? Just cut that out. Paste that in there, and let's see what happens, okay? Now we got A goes, and then C dominates, right? So it's a little bit more balanced, but still not great and not consistent, right? So every time we run it, we get something a little different, okay? So this is kind of the black magic of balancing out performance amongst these threads. We have to study the code. We have to look at our locking strategy and decide, do we want to keep all of our salespeople equally busy all the time? If we do, then we might have to play around with how and when we acquire that lock, okay? But once you get it, it's a beautiful thing because now you're really humming along and you're using all of the awesome power that your, $5,000 computer has to offer for you, okay? Okay, so next time we will just take a look at detaching threads and some conditionals, a couple other things, launching threads inside of constructors. We're not actually going to do that for homework 8, but it is an interesting thing to actually study, okay? So our lab today is not too hard at all. Really, it's just we have 2 guesser threads. So our worker function is a guesser thread trying to guess a secret number. And the secret number is like our inventory. It's being held by the main thread. So our guesser threads are just going to guess randomly and then report whether they guessed or they didn't guess. And they got to know whether the game is over or not, right? So we're going to need to know whether or not somebody already guessed the game. So we're going to need a game over kind of flag as well. So let's just quick take a peek at the code and I'll let you guys get on with what you got to do. Okay, so here's our do guess. So the secret number is there. Actually, this is how we're doing it. We're going to have the secret number in there so that the worker thread can actually know whether it's correct or not. We'll have a mutex pointer. We'll have an ID for the thread and whether or not a winner has been declared. So if you guess the number correctly, declare yourself the winner so that everybody else can tell that the game is over, okay? So that's the idea. I'll leave you guys with that. I got this code in here because I know it's hard to remember. But otherwise, we're just going to launch a couple threads and see who wins first, okay? So I'll leave you guys with that. That one's not optional, but I'll be pretty lenient on submission on that because I know you got your chess coming up on Tuesday. Okay, thanks everybody. Hang in there. I know things are starting to get tense. I'll see you guys on Tuesday.